Hello again. We are going to look at the last lecture of week 3 today. So, the focus of this week has been two things. One is data flow coverage criteria on graphs. And then what we did is we went back to structural coverage criteria, saw how to model source code as control flow graphs, and how the various structural coverage criteria applied over them. Today, what we will do is that we've learned several graph coverage criteria, structural and those that deal with data. And independently, if you're familiar with a little bit of software testing, you would have heard several classical terms in testing: branch coverage, cyclomatic complexity, and so on. What we will do in this module is to see what are the terms that we have learned till now. How are all of them related to classical terms in testing? In this process, I'll also point you to a couple of other good books in testing that you could use for general reading. Part of the material from these courses is derived from those books. So, for today's module, we will not use the book by Paul Amman and Jeff Ofoot. Instead, we will see testing as it has existed for the past 4 decades or so. What are the classical terms? And how what we have done till now relates to these classical terms. We know that the source code model can be written as a control flow graph, as a graph model. What are the other models of the graph? The other common model of the graph is the data flow graph. The kind of data flow graph that we saw in this course took the control flow graph, augmented it with definitions and uses. There's another kind of data flow graph that people use in program analysis. That is, each node in the data flow graph is actually a tuple representing the actual values of the various variables. So we will not really look at data flow graphs for the scope of this lecture. There are several other graphs, interprocedural call graphs, execution orders, as I told you in the last lecture. What would we be doing today in this lecture is to go back and focus on the control flow graph model of a given piece of code and then understand what are the testing terminologies that have traditionally existed. Traditionally means, somewhere from the mid 70s, people have looked at these testing terminologies that we will be seeing today. So, for about 4 decades, they've been around, very popular, very well used. And we'll also understand how structural coverage criteria on this control flow graph relates to these classical terminologies that have always been used in testing. Right. So, what are some of the classical terminologies that we will be looking at and relate them to graph coverage criteria? You might have heard some of these terms when it comes to white box testing. Yeah, that's another thing because we are looking at code and we are looking at structural coverage of code, we are within white box testing, right? So, in white box testing, some of the popular terminologies that exist are what is called code coverage. Code coverage means it says you cover the code in some way or the other. In that, you could do statement coverage, which says that you write test cases that will execute every statement in the code. You could do branch coverage, which says you write test cases that will exercise each branch in the code. You could do decision coverage, which will say you write test cases which will exercise each decision. The various decisions could be those that reside in if statements, as conditions, in loops, and so on, right? Or you could do what is called modified condition decision coverage, MCDC, or you could do what is called path coverage. Things like decision coverage, MCDC, and all are very popular terms that are used to test what are called safety critical software. So, we will see what these are and how they relate to the coverage criteria that we have looked at till now. Another popular term that you would have encountered while you did testing was what is called cyclomatic complexity, right? Related to cyclomatic complexity, people look at what is called basis path testing or structural testing. Another popular term in testing is data flow testing that directly deals with data flow coverage, mostly as we have dealt with in the course. And then another popular term is what is called decision to decision, abbreviated as DD path testing. So, what we will do is that we'll take each of these one after the other, except for data flow testing. I will handle data flow testing separately as the first module of next week. So, we look at the other things, which is coverage, cyclomatic complexity, and DD paths, and see what they mean as far as their relationship to the kind of structural coverage criteria that we have seen till now. As I told you, we assume that we have a piece of code and we have derived the control flow graph of that code, right? In the last module, I took the statistics program example and showed you how to write the control flow graph piece by piece. In the module before that, we saw pattern matching example and we saw the control flow graph and the data flow graph corresponding to the pattern matching example, right? If you are working with control flow graph, then what we saw as node coverage criteria over graphs is the same as the statement coverage. Why is that so? Because if you see through examples, the control flow graph, what does each node or vertex in the control flow graph correspond to? It corresponds to one statement or a set of statements that occur in sequence without branching in between them. So when I say my test requirement is node coverage, what I mean is execute every statement in the graph. So what is popularly called as statement coverage is basically what we refer to as node coverage. Similarly, edge coverage is the same as branch coverage. So branch coverage says you take every branch in the graph, right? So every branch, where do branches come from? They come from if statements, they come from loops, they come from switch case statements, and they result in various edges that go out of the graph. So when my test requirement is edge coverage, then basically I'm looking at branch coverage of the corresponding source code. And then finally, loop coverage is another term. In white box testing, they say you write test cases that will cover every loop. It will skip the loop, it will execute the loop. Once it will execute the loop a few iterations within the maximum number of iterations allowed by the loop. We all know that we saw prime path coverage. So prime path coverage as a TR is basically the same as loop coverage in the underlying piece of code. Right? Now, if we go back to the previous slide, in the various coverage criteria, we've understood statement coverage, branch coverage, loop coverage as an extra thing. Path coverage could be thought of as partly doing loop coverage. We said we won't explicitly look at complete path coverage, right? Because several times it turns out to be an infeasible requirement. So we did prime paths. Today I'll tell you a few other kinds of path coverage criteria. What is left? Decision coverage and MCDC. Decision coverage and MCDC we will look at when we do testing with logic predicates as our models. So when we finish graphs, right, in a few weeks from now, the next module that we will be beginning is to assume software artifacts as various kinds of logical predicates, and we'll design test cases based on those logical predicates. So when we do that, the coverage criteria that we see there would correspond to decision coverage and MCDC. Moving on, the next popular testing term that you would have heard is what is called cyclomatic complexity. It's a pretty old term actually. It's more than 4 decades old. It was introduced by this person called McCabe in the year 1976. So what is cyclomatic complexity? It is a software metric. What is a software metric? Software metric is some kind of a measure about the piece of code that we have in hand. The most popular software metric is what is called lines of code, and usually for fairly big software that are deployable in for commercial purposes, lines there are several thousand lines of code. So we say kilo lines of code or KLOC for every 1,000 lines of code. That's the most popular software metric. So we say a large software has several KLOCs, means several thousands lines of code. Another popular metric that is used to measure how complex a software is what is called cyclomatic complexity. Here, complexity is not measured in terms of the number of lines of code, it is measured in terms of the number of various branches that can occur in a software. So, what does cyclomatic complexity represent? It represents the number of linearly independent paths in the control flow graph of a program. A testing that deals with cyclomatic complexity is what is called basis path testing. Basis path testing basically enumerates the number of different linearly independent paths and then tests with reference to the cyclomatic complexity of the program. So, what we'll spend the next few minutes on is trying to understand how exactly to compute cyclomatic complexity given a control flow graph of a code, and what does basis path testing as a class of testing, a category of testing, correspond to testing it with reference to the cyclomatic complexity measure. So cyclomatic complexity, as I told you, deals with a number of linearly independent paths. So we first need to understand what is a linearly independent path. What is a linearly independent path? It's a path that does not come as a subpath of any other path. So you take the control flow graph of or the CFG of a program, there'll be several paths in the graph. Linearly independent path is similar to prime paths. If you see, prime path is a path that doesn't come as a subpath of any other simple path in the program. Linearly independent path is a path that doesn't come as a subpath of any other path in the program. So except for the fact that the word simple is not there, linearly independent paths are the same as prime paths, right? So what we do is, how do we compute the cyclomatic complexity? We compute the cyclomatic complexity denoted as M by using this formula. So it says M is equal to E minus N plus 2P. What is E? E is the number of edges in the control flow graph. N is the number of nodes in the control flow graph. What is P? P is the number of connected components in the control flow graph. How do I obtain the control flow graph? When I calculate E, N and P, I make one important assumption about the control flow graph. You remember when I told you that when you have a series of statements, let's say assignment statements or printf statements, one after the other, you have the choice to keep one vertex or one node for each statement, or you have the choice to collapse these series of statements as one vertex, one individual vertex, assuming that there is no branching in between them. So such a series of statements is what we called a basic block. And when we drew control flow graphs of several code fragments in the last module, I assumed one vertex for every basic block. For computing cyclomatic complexity, that assumption turns out to be very important. This formula will not be correct if you don't assign one vertex for one basic block. If you take the other approach where I assign one vertex for every individual statement, then this will not be the formula for cyclomatic complexity. So cyclomatic complexity assumes that the control flow graph is drawn in such a way that each node represents a basic block of statements. And different nodes exist only when there is a need to branch out of that node, only when there is a decision statement out of that node. Under that assumption, that's how we've built most control flow graphs throughout our lecture. So for all those control flow graphs, the formula to compute cyclomatic complexity is this. Very easy to remember. It is E minus N plus 2P, where E is the number of edges, N is the number of nodes, P is the number of connected components, right? For graphs that correspond to a single program, a single procedure or a single method, assuming that there are no interprocedural calls that I model in my graph, then if you remember, the control flow graph looks like one large connected component, right? It doesn't have several bits and pieces of disconnected components. If I consider that, then this last term, P, which is the number of connected components, is basically one for a graph, control flow graph that corresponds to one method, right? So the formula for cyclomatic complexity becomes simpler. It is E minus N plus 2. So it so turns out that the cyclomatic complexity of a program with only one entry and one exit, means with only one initial vertex and one final vertex, is the same as the number of decision points. What are decision points? Points where there is branching out, if, switch, and so on. So number of decision points contained in that program plus 1. So what it says is that how do linearly independent paths come? I go through a series of statements. At some point I branch out. When I branch out, I have a choice. I take the left branch or I take the right branch, assuming that it's the branch of an if statement with an else part. So each gives rise to one linearly independent path. And what happens is that cyclomatic complexity of a program is basically the number of such branches plus 1, and it exactly gives the number of linearly independent paths in a program. And they say that usually a good indicator of a good software that is easy to maintain and easy to handle should have cyclomatic complexity somewhere between 1 and 10. Cyclomatic complexity of 1 means the software has no branching. So it may not be very useful to look at such software. So cyclomatic complexity should be typically between 2 and 10. Any number less than 10 is considered to be a good cyclomatic complexity for a piece of software when it comes to maintaining and handling that software. Right, so here is a small example. So this software, this is the control flow graph corresponding to some piece of code. It has exactly one initial vertex marked here. it has one final vertex marked here, and then it has two if statements. There's one branching here, which branches out to this node and this node. There is one more branching here, which branches out to this node and this node. So there are two if statements. If you count the number of edges in this graph, there'll be 8 edges and there'll be 7 vertices, and this whole graph is like one connected component. So the formula cyclomatic complexity turns out to be 3, right? If you see how many branches are there in this graph, there are 2 decision points, one here and one here. So what did we discuss here? We said the cyclomatic complexity is the number of decision points plus 1. That's true for this example, right? It's the number of decision points plus 1, which is 3. Right? So there is another popular way of checking for cyclomatic complexity. What people do is that suppose this turns out to be the control flow graph of a particular program, right? What they do is they put a dummy edge back from the final vertex to its initial vertex, like this. You trace, assume that I'm tracing an edge back from the final vertex to its initial vertex. After doing that, the graph becomes one strongly connected component, right? You remember what strongly connected components are? We looked at them in the graph algorithms lecture. Strongly connected components are those components in which every pair of vertices are reachable from each other. So under that assumption, cyclomatic complexity also turns out to be E minus n plus 2, basically because of the same reason. There's exactly one connected component, which actually happens to be strongly connected also. So cyclomatic complexity becomes simpler. I don't have to compute connected components. It's usually easier this way because if you have something like this at the cost of adding a few extra edges, then you don't have to run algorithms that compute the number of strongly connected components as subroutines. You directly count the number of edges, number of vertices, which are usually easy to do given a representation of the graph. And there you go, the cyclomatic complexity is easily measurable without calculating any strongly connected component. So usually this measure of cyclomatic complexity is preferred, and it's popularly known as the cyclomatic number. Some books and papers also call it the Betti number. So now let's look at basis path testing. As I told you, basis path testing tests the cyclomatic complexity of a piece of software. What it basically does is it enumerates all the linearly independent paths in the graph, or in our terms, it enumerates all the prime paths in the graph. And for each such path, this is your TR, your test requirement. And any set of test paths that satisfy this TR would hold good for basis path testing. Because we've looked at prime paths and enumerating prime paths, I'm not revisiting any algorithm that will enumerate linearly independent paths. It's very similar to this. So we consider the same algorithm that we did for prime paths as working for enumerating linearly independent paths and test it. And like we did for prime path coverage, basis path testing subsumes branch coverage or edge coverage. Complete path coverage in turn subsumes basis path testing. If you're confused, what I'm trying to say is that basically linearly independent paths correspond to what we saw as prime paths. The only difference is simple paths versus non-simple paths. So basis path testing is more or less the same as prime path testing. So how will I come up with a set of test requirements for basis paths? What are basis path testing test requirements? Enumerate all the linearly independent paths. It's the same as enumerating all the prime paths. So I'll use the same algorithm that we saw for prime paths to enumerate all the linearly independent paths. That's my test requirement. And then I come up with the test paths that satisfies the test requirement exactly in a way similar to the one that we did for prime path testing. Right? So the last one that I wanted to deal with, another popular term that has been used in testing, is what is called a DD path or a decision to decision path. This is different from basis paths or linearly independent paths or from branches or from any of the kind of paths that we have seen throughout the span of this course. So in short, what is a DD path? A DD path is a path of execution between two decisions in the CFG. The books that talk about DD paths usually call the control flow graph as the flow graph or a program flow graph. But if you're confused, please remember that it's the same as what we call a CFG. At the end of the slides, this module, I'll point you to good references where you can read more information about cyclomatic complexity and about DD paths. For now, we will just introduce what a DD path is and say how we could go about testing for DD paths. So here is a small control flow graph. Its initial vertex is 1, final vertex is 6. And where are all the branches? There is a branching here at 2. There is a possible choice of going to 3 or going to 5. And from 3, you can go to 4. There's no choice there. And if you see 6, there are two ways that you could use to come to 6. You could have come from this 2, 3, 4, and 6, or you could have come by using 2, 5, and 6. So I consider 6 also as having a decision point, as a representing a decision point in the graph, 2 as representing another decision point in the graph. Why? Because for both these kinds of vertices, there is a choice about either coming in or going out of the vertex, a choice of more than one way to come in or more than one way to go out. So these are what are called decision points in the graph. And DD path says your test requirement or TR is the set of all paths between two decision points in the control flow graph. So to see what a DD path is in detail, we will need the notion of what is called a chain in a graph. You might have heard about the term chain when you looked at what are called partial orders. You typically see partial orders in a course in discrete maths, let's say. Chains are what are called total orders there. For the sake of simplicity, I'm redefining chains here. So what is a chain? A chain is a path which satisfies the following two conditions. The initial vertex and the terminal vertex of this path are distinct, which means it's not a loop, it's not a cycle. And then all the interior vertices. What are interior vertices? Interior vertices are those that are not the initial vertex and not the final vertex. Everything else in between, that comes in between. All the interior vertices have both in degree and out degree as 1. So if you try to visualize how this chain will look like, it will look like one long path in the graph from a unique initial vertex to a unique final vertex. And what is a maximal chain? A maximal chain is a chain that is not a part of any other chain. It's somewhat like prime paths, right? A prime path is a path that is not a subpath of any other path. So maximal chain is a chain that's not a subchain of any other chain. So what is a decision to decision path or a DD path? A DD path is basically a path of vertices in the CFG that satisfies any of the following 5 conditions. If it satisfies any of these 5 conditions, we call them all as decision to decision paths. So let's look at the conditions one after the other. So it could consist of a single vertex with in degree 0. If you think about it, visualize in the CFG, which is that vertex that has in degree 0? What does it mean for a vertex to have in degree 0? There's nothing, no edge coming into that vertex. The only vertex that has in degree 0 is the initial vertex. Then it can consist of a single vertex without degree 0. Again, if you visualize our model of a control flow graph, which is the vertex that has out degree 0? It is our final vertex or a terminal vertex. And then decision path can also consist of a single vertex with in degree greater than or equal to 2 or out degree greater than or equal to 2. If we go back to the example graph that we had, vertex 2 is a vertex with out degree as 2. Vertex 6 is a vertex with in degree as 2, right? So both vertices 2 and 6 satisfy this condition. And both represent some kind of decisions. That's what I was trying to explain a few minutes ago. Right? Decision path can also consist of single vertex with in degree and out degree as both 1. Right? Or a decision path could be a maximal chain of length 1. So just to clarify, in case you find it confusing, what is a decision path? Basically, it's a path that takes you from one decision to another decision. As I told you, when we consider decisions for the sake of DD paths, decisions could be of two kinds. They could be of the classical kind like this, branch out, or they could be of the kind where there is decision for branching in, for coming in. So what it says is that DD path lets you go from one decision to one decision. So it clubs the vertices as all these things. It says the initial vertex is one separate DD path. Final vertex is another separate DD path. Then all the decision vertices, which are vertices with in degree greater than or equal to 2 or out degree greater than or equal to 2, are separate decision paths. And then in between, if I have a single vertex with in degree 1 and out degree 1, then that's another decision path. And then the other kind of decision paths could be chains of length 1, right? So if I apply this definition to this example graph, how many decision paths, DD paths, will I get? The initial vertex 1 is 1 DD path, final vertex 6 is 1 DD path, the decision vertex 2 is a separate DD path, the vertex 5, which has in degree 1 and out degree 1, is another DD path, and 3, 4 is a chain of maximal length 1. So this is another DD path. So totally for this graph, there are 5 DD paths. Initial vertex, final vertex, the decision point 2, vertex 5 which has in degree and out degree 1, and the maximal chain 3, 4. Right? All of these satisfy one of these conditions. That's what is written here. The example graph that we saw has 5 DD paths which are listed here. Right? So we will not really see how to enumerate DD paths and how to test them and all, because they're slightly out of scope for this course. But if you're interested in knowing more about it, this is a very good book to learn more about DD paths. It's a book called Software Testing, a Craftsman Approach by Jorgensen, and a recent edition is available. For getting to know about basis path testing and cyclomatic complexity, as I told you, McCabe is the founder of cyclomatic complexity. He has an NIST report. NIST, if you remember, is National Institute of Standards and Technology. He has an NIST report which details how to find cyclomatic complexity, how to do basis path testing, and how to use cyclomatic complexity for object-oriented software, for integration testing, and so on. It's a pretty good article. This another popular testing book, the book by Robert Binder, which focuses on testing object-oriented software, also has an exhaustive discussion on cyclomatic complexity and basis path testing. So if you're interested, you could further read on from any of these books, and feel free to ping me in the forum if you have any clarifications or questions that you would like me to answer. Right? But the main focus of this lecture was to help you understand that there are several classical terms that are present, like the terms that we saw today, and see what they are and how they relate to whatever we have seen till now. So I hope you're not confused about why am I seeing these graph coverage criteria and how does it relate to cyclomatic complexity. And I hope this lecture would have helped you to understand and answer some of the questions that you had in your mind. Thank you.